I'm going to kind of kick it off with just some slides that I put together. We've also got one of the resident experts at 20793 in the room with us, now Dr. Sam Russell. So happy to have you here, Sam. But really this is just to get the juices flowing, and I hope that what will come to your mind will be questions that are along the lines of, why do we care about JSC 20793? Why are we spending so much time investing in 20793? And is it even applicable beyond space exploration? So that's my goal for this talk. And then, with that said, we'll get going. A little late, sorry. So let's talk about thermal runaway and its causes. I always enjoy, before talking about battery safety and design requirements and the practicalities of that, I really always think it's important, especially when you have a broad audience like this, to just take a minute and level set with what are we actually talking about when we say thermal runaway. And what I mean by that is beyond what we see on 10 o'clock news, beyond, oh, okay, I see a battery fire on the news, or here's a burnt up scooter picture, or whatever it is. Fundamentally speaking, what are we talking about? Because you have to understand the fundamentals before you can really dive into why are the requirements written in the way that they're written, and why are they frankly so stringent. So when you talk about thermal runaway, if you start at the right-hand side and work your way back, what are we talking about? We're talking about the rapid exothermic decomposition of the materials within the cell that drive temperature rise up within the cell at such a rate that eventually that cell loses thermal stability. It eventually ruptures. We have flame, ejecta coming out, solids, liquids, and gases come out of the cell. We can have secondary combustion events that then happen as a result of that, whether that be there are nearby combustibles that are available or the materials themselves coming out of the cell mix with the gases and ignite the gases. We have additional combustion events which add energy and fuel to the system. So that's what we're talking about when we talk about thermal runaway, but there's a lot of things that can actually lead to thermal runaway occurring. From a design perspective, the first is we could have some level of mechanical layers to touch and create a short circuit. There's actually a really great example of that in our trophy case from a ballistic test that we did. So we did a great job of designing armoring that did exactly, or working with a vendor to get armor designed that did exactly as anticipated, but with the deformation of the armor, we have a lot of crushing going on in the cell, which if you're not careful can lead into a thermal runaway event. We call that mechanical abuse. An example of that you may see in a real world example, without a skid plate, you could see the batteries in a car get dented or damaged. If that car bottoms out and it's a lower facing battery pack, why do we have those skid plates? To prevent mechanical abuse from happening to the battery. You think of eVTOL, a big thing that you got to worry about when you're dealing with electric aviation and aircraft is, impact, whether that be intentional or unintentional impact. What damage could be sustained to the cells mechanically that could then result in those electrode layers touching and result in a thermal runaway. So ultimately, you're going to have requirements, whether you're dealing with e-aviation batteries, space batteries, military batteries. You're going to have regulation and requirement that mandates that you're going to have structure that deal with potential mechanical abuse and minimize those risks. Next, you have electric abuse. These are things that we can prevent with software, with BMS, and then with also protection to our busing and various fusing, but effectively overcharging the battery, going to too deep of a discharge of the battery, over voltage, external short circuiting. Internal short circuiting can also sometimes fall into the electrical abuse category depending on who you're talking to. But effectively using the cells electrically in a way that they're not intended to be used can result in formations within the cell that can also result in the connection of electrode layers or current collector layers, thus resulting in a thermal runaway event. And then you have thermal abuse. Some of the experiments I talked about earlier, we trigger thermal runaway using heaters or using the adiabatic heating of our bomb calorimeter, for example. That's because if those materials within the cell reach a certain threshold level, they begin decomposing. So what that means is a chemical reaction begins happening, but it only happens at that elevated temperature. Problem is, when you get to that elevated temperature and those reactions start happening, they're also exothermic. What that means is that while the material is decomposing, it's also generating more heat. So it kind of becomes a bit of a self-fueling situation that you're dealing with that rapidly speeds up and results in loss of stability and eventual thermal runaway. But again, so we treat thermal abuse as that third cause or trigger, if you will, of thermal runaway. So you get the cell to the elevated temperature because you are abusing it thermally, whether you're cycling it too hard and it's heating up naturally, or you're operating it in an environment that it should not be operating at. The cell heats up, materials decompose, you run the risk of thermal runaway occurring. Now, what's good about each of these three areas is that with sound design practices and principles, and with good requirement sets, we can actually avoid all three of those altogether. You can avoid mechanical abuse, you can avoid electrical abuse, you can avoid thermal abuse, but what you can't avoid with a perfect design, even with fully work instruction 37A screen cells, like we talked about earlier, is you can't avoid the possibility of an internal defect to that cell eventually leading into a thermal runaway event. That's why even NASA, with probably the highest quality cells you could possibly fly, still fly crew rated missions with PPR packs with flame arresting devices. It is because there's always that possibility of a latent defect leading into thermal runaway, which then goes through this entire process, thermal runaway, and then if you don't have flame arresting device, you have combustion happening, which if you're talking about spacecraft, you're in a pretty isolated environment. I have a fire in this facility, I can leave, my crew orbiting the moon can't exactly come home, right? So that's why we have to protect against this. So again, just to level set, I'm gonna replay a video from earlier. This is an example of a nail penetration experiment leading into thermal runaway. Nail penetration is a bit of an over-test to represent an internal short circuit. The idea is, you're puncturing a very targeted area of the cell that is then leading the cell to enter into thermal runaway from that initiation point. Fundamentally speaking, it's also a form of mechanical abuse because you're pushing all the layers into each other with the nail. So if you want to get into a debate on that, certainly could do that over lunch today, of triggering methods and their merits. The point is, you use one of those methods. I could just as easily throw a heater video up. I could just as easily throw an overcharge video up and show you the voltage draw, or the voltage pumped into the cell, the current pumped in the cell, and then boom, it goes. But the point is, you follow one of these triggering methods, the cell is going to go into thermal runaway, and then we got that to deal with, right? Backing that up, we can design for all those failure modes, but we can't design for the internal defect. So we have to have designs that deal with that. Again, propagation, let's talk about that for a minute. So this is RoboSimian. I figured since NASA's here, I'm gonna pick on them. The reality is even in highly controlled environments, thermal runaway can happen. So this is a RoboSimian battery. If you watch the time clock here, you see a period of time where the engineers are literally standing right here when the battery goes into thermal runaway. So you can imagine what could happen to personnel in the area, right? This is why we care about battery safety. Whether I be talking about a car battery, an e-bike battery, something that my kids are playing with, or something that's flying to the moon next year or in a few years, this is why we care. This is why we make safe battery designs, right? Oh, I'm sorry. What you also see happening in this event is an example of these failure modes are not just thermal, these are chemical in nature, right? So you actually saw it, if you watched the beginning of it, I believe it was an intern who came in, yeah, he's right there, he's trying to put it out with fire extinguisher, and what does it do? It keeps reigniting, right? And that's because you got to remove the heat, because at this point, all the neighboring cells have been thermally abused, right? So they're entering into rapid exothermic decomposition, triggering into thermal runaway. That's why, although the extinguisher is extinguishing the event, it keeps reigniting, and that's because the cells are driving themselves into thermal runaway. It's not just the flame's going. So that gets into the difficulties of dealing with battery fires, which we've actually got some first responders here with us today who we could have probably some pretty extensive conversations about that and the difficulties of attending to these types of fires. But again, this is a key example. I like to watch this one just as an example. This is why we want PPR, right? So that initial event going off, that's a bad day. But if you got a flame arrestor and it's just smoke coming out and maybe you lose a couple strings in the battery, yeah, it's a really bad day. But my crew can survive, or my payload can survive, or my application can survive. Everything's gonna be okay. Now, if that happens, on a spacecraft, or if that happens in a car, or if that happens in a house, or with whatever your application is, clearly it's going to be a much worse day, right? So we have to have something that deals with that. So when you're talking about thermal runaway risks, and you're also talking about high cost, high risk applications, which we typically think about with space, aerospace, and defense, it's important that you deal with thermal runaway. And that's what our regulators are working to do. For NASA, for space exploration, we're talking about addressing those risks with the crewed space vehicle battery safety requirements, JSC 20793, which is on revision D right now. I'll have some conversation on that later today. You could just as easily look at regulation for other industry as well, depending on which regulatory body. FAA, Tom, you got to deal with those guys. For me in transportation, I got to deal with DOT. Every regulator is going to have their own differentiating set. In this case, talking for space batteries, and in particular over 100 or over 80 watt hours for crewed applications, we're dealing with JSC 20793. Given that a lot of what you're going to see today is 20793 centric, and what I mean by that is something that I can use, a tool in my toolbox to satisfy some requirement in this standard, we thought it would be helpful to just take a minute with everyone, with such a broad group of folks, to really dive into what we're looking at there. So now if you look under your seat, I've got a 100-page document printed out for everyone. So I'm not going to make you digest it today, nor am I going to give you a long PowerPoint presentation with every single section populated of 20793. I would say it is a public document. I would encourage you, if you are in the process of battery design or you deal in battery safety, I think it's a great one to be familiar with. A lot of good information in there, and in particular, a lot of good design practices that we'll talk about later today. But ultimately, I think there's three key sections that you're going to find when you start digesting it. The first being general battery safety requirements. And these are basic battery safety requirements for batteries of all kind, right? So the standard doesn't just address lithium-ion batteries, it's going to address primary batteries as well and other chemistries. From there, it's going to have requirements that are addressed in Section 5 for hazards and controls. This is where we'll find some of the thermal runaway specific requirements that apply to batteries that are greater than 80 watt hours, which, by the way, with chemistries of today, 80 watt hours is not a big battery. And so we're talking about a lot of requirement that gets levied on what for today's standard is a pretty small battery. And then in Section 6, we have more detail on just safety relevant to specific battery chemistries. But what I want to zero in on, and what I think is important to a lot of the materials that we showed today, and where I'd like to get some of the Q&A going in this session, is this. And that's for batteries greater than 80 watt hours, we have to have and when I say we have to have, I'm talking about if you are to satisfy JSC 20793. There's a litany of things that you have to do, but from a thermal runaway perspective, you have to have a cell-to-cell propagation resistant design and a flame arresting design. Now, a lot goes into that, a lot of design goes into that, a lot of controls go into that, and we'll talk about that here in a minute, but that's the premise. And then you have to show that you are doing that, and it's a very rigorous testing campaign that you have to go through to show that, okay, well, gee whiz, you designed this battery that is PPR, but what does it actually mean? You got to go prove it and test. And then there's a lot that you got to do in that test, a lot that you have to show, a lot of documentation that you got to have in there to show that this was a good test. This was representative of a worst case scenario field failure.
Why 80 watt hours?
Why 80 watt hours? That's a good Sam Russell question. What is the history on the 80 watt hour selection?
Like most of our somewhat arbitrary metrics, it was originally drawn to exempt the laptops that were on station.
So at the time, laptop batteries were below the 80 watt hour threshold, and y'all didn't want to be going through an entire PPR campaign for every laptop that you fly to station, which I'm guessing is quite a few.
Correct.
And so was a.
If you look back, we did the same thing on coin cells. First it was 300 milliampere hours, then it was 600 milliampere hours, then it's 1 ampere hour. As the technology kind of evolved, our
Right.
baseline, the cost to benefit ratio is out of whack, and we started raising those metrics. So yeah, that 80 watt hour was based on laptops.
And I think that that also the decision to do that also gets into the classification of the risk. So if you dive into 20793, there's a couple classifications for the batteries: non-critical, critical, catastrophic, and how the risks are categorized based on the size of the battery, type of the battery, and the chemistry. And I would assume, in addition to that, part of that tailoring is also to reduce the overhead required for batteries that would be categorized as just critical.
Yeah, absolutely. And then that's one of the changes we want to make with Rev E. It's going to be really hard to get that one through due to all the program proliferation we've had and all the different configuration review processes we'll need to go through. But we did use language, critical and catastrophic.
Mm-hmm.
That's really more in line. It was kind of an echo from the safety community, and they've asked us to change those categories. But it does try to allow some perspective. It's interesting to me, 20793 really kind of represents a framework for battery design. It's grounded in two-fault tolerance, and it's rich with our solutions.
So for those in the room, would you just elaborate just a little bit more on, for NASA and a battery, what we mean by the language of two-fault tolerance?
Yeah, so I started my career in shuttle, and basically station flew in the shuttle payload bay. And to be in the shuttle payload bay, you had to be two-fault tolerant. So your first control is always your design. And then if something breaks, you need to have some other control to mitigate that failure. And then one more broke, you got to have another control to mitigate that failure in a fail-safe mode unless you're fail-up. And then after two faults, you can stop counting, basically. A little irony there, because shuttle itself couldn't have satisfied its own payload requirement. So you did see some evolution of our NPRs as we moved through the Constellation program to try to kind of dial back that a little bit. But it's also kind of interesting because as we're moving away from station and these big kind of programs, we're starting to dabble a little more in scientific missions, Artemis 3, 4, 5. So you're in a human environment, but you're not necessarily a human-centric payload. You're not a life support system. So again, that 20793, that kind of framework, in order to comply with the requirements, sure, you've got to meet them all. But that way of thinking about the battery, the design, and its integration with the system, you can technically, and our book allows you to do this, you can stop at some point. You don't have to go all the way to two-fault tolerance, but when you stop, you've got to get the program or your governing agency to accept the risk that you didn't go all the way through it. So just kind of a different look at the book. One more thought for anybody who spends time in it. We're engineers. We try to write requirements. We write those requirements based on our own experiences, which are largely derived from our own designs and our own solutions. So the requirement set will kind of tend to push you to very specific solutions.
Yeah.
And as technology and the marketplace evolves, those solutions will become less and less relevant, right? We don't use vacuum tubes anymore. Our current control abilities get better. So ideally, there would be more of a logical expression, but that's going to be a really big mountain to climb.
And I think a key example of our own experiences and designs, driving the requirements that drives to specific solutions, right? That would also zero in on, and I would argue these are not bad design practices and principles, but if you really dive into 20793, there are 5 key recommendations that are coming out of that from a design practice, right? So if you kind of have to have these things to truly satisfy 20793. So you got to deal with sidewall ruptures. You got to provide adequate spacing for heat rejection. You got to deal with the propagation. So that means you got to have spacing. Otherwise, if you can't just tape your cells together, you're gonna have propagation, so you're gonna fail. So that means, okay, well, I got to space things out. And if you got to deal with your ejector, you got to have space there. So it kind of requires you to do that. It kind of puts us down the path of individually fused parallel cells, prevent external shorting, protection of the adjacent cells from the TR ejecta, which then drives us to have top capture plates with burst discs on them. And then the 5th recommendation, being preventing flames and sparks from exiting the battery and enclosure. So, I guess on your train of thought, it sounds like, as the requirements were developed, there were also designs that satisfied some of these guidelines, and maybe some of that heritage and engineering expertise on that helped lead to the requirements that were written in 20793?
Oh, yeah. We definitely learned by trying, right? And so specifically, you're helping me kind of course correct. I also tend to ramble, so cut me off. But you're talking about 5 elements to satisfy one cause of catastrophic battery hazard. We typically look at 5 causes of battery hazard, so each one of those causes will have multiple elements. Yeah, so I kind of forget where I was going there.
I cut you off.
I do know this.
No, I cut you off, and then I canceled the organic flow, man.
No,
we'll get back on it.
You're good. I guess my one final thought there, if I can pull something out of a hat. Real quick, it's very back to my kind of solution thing. Those 5 guidelines that you talked to, the 5 design guidelines for non-propagating batteries, where those came from. So when we were doing the development work, basically you mentioned 787. It was really the hoverboard that convinced program managers to care. So 787 eroded our confidence in custom batteries, right? Up until then, we could take a high quality supplier. You know, there's some Japanese companies that build really high quality stuff, and we would kind of pass them through the system because, you know, that quality element was considered good enough. Well, 787 eroded that view, right? All of a sudden we were like, oh no, that it's not good enough. Yet again, you still have program managers controlling budgets. But when they bought the hoverboard and put it under the Christmas tree, and then they're calling you going, now how the heck am I supposed to charge this thing because they're catching on fire everywhere? That's what did it.
That's when it's like, okay, we need to deal with this.
It got personal.
I can't even charge my kids Christmas gift.
Yeah, exactly.
And I remember when that first started happening, even, sorry, not to really derail, but even Amazon had to come out and pull a bunch of stuff that had been floated for sale when the hoverboards first started becoming a thing because of all of these fires. They were even kind of dealing with that aftermath of, oh no, what do I do?
Right.
You know?
So when the way we approach that is Eric and a team, which I was kind of a part of that, but more on the project management side, they would go through the prototyping phase and then turn it over to the design team, the flight team, to mature it and fly it. And so each handover had a certain number of rules that went with it. Like, you're going to change some things, but don't change this.
Right.
Right. And then the next one handed over, because it was a different form factor. Don't change that thing I just told you, but now don't also change this thing. And over the course of probably 5 iterations, roughly, we ended up with the 5 design guidelines, and they got potted and pushed out to the world. But again, very solution-oriented, right? So you read it, and you think you can meet it, and everybody gets really confident and goes and tries to meet it, and then their battery propagates. And so there are elements to that relationship balance that are not purely expressed in those few little dimensions, right? Or your interpretation of those words. So it is interesting. It's been a fun road watching all this, and you guys have been doing great work. So anyway, I'll stop wandering.
No, you're good. This is good. And I would say, just one thing that I'd like to put in everyone's mind, just on the challenge of these 5 recommendations, which by the way, I'm here to say that there are a number of these that I'm a firm supporter of. I've been one of my first battery I supported. We redesigned the Orion battery, which that particular version, the battery will now fly on an Artemis 2. Redesigned it to follow a lot of these design guidelines. But one of the challenges that you deal with on this is these are good things, but it's all good things to solve one problem. Right. And it also adds a lot of mass. So I know we have Tom here from BI. When you talk about flying batteries, energy density is king, right? And so if we're also saying with our requirements, hey, you got to deal with thermal runaway, and specifically you got to deal with this one problem, we're also saying you've got to deal with this one problem that, by the way, requires a lot of overhead to deal with. If you look at a lot of the off-the-shelf batteries that are available today, they're flight ready, from even some of KULR's competitors, but they're certainly not PPR. And why is that? It's basically a bunch of cells strapped together, capture plates on, PCB that controls it. Listen, for a battery that is not intended to be PPR, these are good batteries. But if you want to make the jump, and by the way, these are devices that customers are used to working with it. And when you start talking about like small sat, CubeSat, secondary payload batteries, people are used to working with just these innately lightweight, small batteries that are just going to fit in this little nook and cranny of their spacecraft, to now having requirements that we have to satisfy, like 20793, where now all of a sudden it's like, gee whiz, I got to have a housing now for my battery because I got to do ejecta management. I got to have flame arrestor because I can't have any fire going off. I got to do all this abuse testing, right? It creates challenges. And so one of the challenges with dealing with the PPR battery, and specifically addressing 20793 and meeting these design criteria is, I mean, look, anybody out there can design a brick, right? You could go design a brick and deal with these things very easily, and your brick's not going to fly. So that's the challenge too, is how do you balance the energy density of the pack and the margins you have on that with the safety that you need to achieve. And then how do you balance that with an ever decreasing allowance available based on our consumer applications of, maybe it used to be you were allowed to have about a 30% mass ratio, 30% of the pack could be. But now maybe it's, well, you can have 20. Well, now maybe it's 18, maybe it's 16, and it just keeps going down and down and down. Now we have a little bit of conflict, I would say space, aerospace in particular, on this conflict of dealing with thermal runaway and the parasitic mass that's required to do that, because indeed it does take mass, with the energy density requirements of the mission.
Can I ask a follow-up to that?
Yeah.
So in opening up the aperture for 20793 outside of crewed space, are there benefits for performance as well besides safety and looking at defense or commercial applications?
So are there benefits beyond just the safety of following the 20793? Sam and I were talking about this actually before this event, and we were talking about reliability. So if you get back to even cell screening and the matching that we do with Work Instruction 37A and getting those cells ready, you're ensuring, okay, I don't have counterfeit cells. You're ensuring that I've done everything I can to reduce the risk of having a cell built into my pack that has some level of FOD or internal defect. But there's also another benefit of doing all of that work is you're going to come up with a highly reliable design with some of the most reliable cells that you can get based on testing data that you can collect, which ultimately will help drive you towards a pack that's operating based on how you operate it, not necessarily just a 5-year profile, but I think NASA, you guys are looking at batteries that have to operate for 15, 20 years sometimes. And so by following some of these standards, you result in a highly reliable pack.
And again, you're suffering a bit from our progression, right? Back in 2007, screening was our only way to reduce likelihood, because back then there was a lack of agreement within the community about whether this failure was even realistic, right? Like a lot of your field failures are due to pinched power wires, not batteries going upside down. So yeah, we baked into our requirements a reliability aspect to reduce likelihood, and then we added that consequence reduction to the design.
Yeah.
So yeah, you get both aspects.
Is there multiple triggering mechanisms, or you just go with heater tape or L or what?
So I think traditionally we use heater tape, but I think most people that I've experienced or interacted with on 20793 were using trigger cells. So we talked about that ISC cell. So just a little bit about that. So a trigger cell is a cell built with the NASA NREL invention that allows the cell to enter into thermal runaway at much lower temperatures. And this is actually a technology that Mike Carpenter here in the back oversees for the company. So has a wax phase changing material that melts at a designated temperature, allowing a copper puck inside to create contact between the layers. Very reliable form of triggering thermal runaway, which induces an event very similar to an internal short circuit, just as in the name.
So that you don't have to heat it up to 200 C.
That's right.
Go at like 55 or something like that.
So a lot of these designs, we're talking about marginal success here. It's a game of straws, right? Especially when you get to some of those super energy dense packs, right? And so you don't want to just bake out a trigger cell to 150, 180 degrees Celsius and allow those neighbor cells to just soak in all that heat, because now you've biased what would be a perfectly good test and a perfectly good design to fail propagation in a way that's completely unnatural from what you would see in a field failure event.
Yeah, because I participate in some of the UN meetings where we're looking at coming up with test methodology and criteria for battery design to incentivize industry to do this kind of PPR designs. And some of the negotiations with this group of people are saying we got to heat to 375. it'll probably go before that, but they're just afraid there's some cells that are just never gonna go. And I think if you heat the 375, it's a benign cell.
Yeah.
You give me a break, right? But
Yeah.
the problem is, you're artificially influencing the other cells that are in your test fixture. So, you don't know what's gonna happen.
It definitely creates an overtest, and I think that that's an area where we have to be cautious, particularly when trying to qualify design via abuse test, is to ensure that our test plan and procedure is not reflective of an overtest. There's a big difference between overtest versus worst case scenario test, and so you want to rely on the latter when you're qualifying your pack, and kind of yes.
It's interesting for us as first responders to hear about the design itself, because there's so many different items out there on the market to stop the propagation from one cell to another, and whether it's piercing nozzle or ways to target certain areas of the battery, that we're all trying to struggle to find out what works best and what's safest. So I'm interested to hear more about the design itself, because we know we can cause a lot more problems by putting water in the wrong places.
Absolutely.
Than we typically would. So.
And when you're dealing with it, right, it's a challenge. You wanna stop the event, and water does a great job of doing that for us, right? It deals with the heat. Having a coolant that evaporates, you get the benefit of latent heat of vaporization. It's great, but of course, water being conductive creates some other issues, I would say, for a larger fire that we could be dealing with. And so, certainly, hopefully, as you go throughout the day-to-day, you'll see just some of the strategies that we employ on our batteries. And then also, you'll learn more about just the science behind thermal runaway and what's going on, which in turn could help as you develop your response practices, right? Yes, sir.
What about the effect of soak temperature and state of charge in terms of how things should be tested? A lot of times things just get tested at room temperature, but we may see very different propagation behavior at 50 degrees C or 70 degrees C. And what should be our upper limit? What should we be testing to? And the kind of the intuitive thing is the higher SSE is the most dangerous, and so take everything to 100% or 105%. What's your comment on those two variables?
Yeah, so state of charge and temperature. I'll start with state of charge. I would say I think it's always important to do your final testing with full system level build at 100% state of charge, which is also reflected in 20793, and that's simply because that could happen. You're charging your battery. It's worst case. Everything could be at 100% state of charge when an internal defect leads to short circuit, and so you certainly have to test for that. On the temperature side, I think that is certainly an area where you should always attempt that test. I think it's important to understand where your battery fails at that upper threshold. I think it's important to focus on doing that upper temperature at a soak temperature that reflects your mission, not necessarily the maximum operating temperature of the cell. Now, if you have analysis that guides you to say, okay, this is my max operating environment, and this is the temperature of the cells when they are cycling in that environment, then certainly, you could do some tailoring to ensure that the cells are at that elevated temperature. And Sam, I was kind of doing a recent read through of 20793 myself, and I was also looking at reports from other batteries. Is it a hard requirement to soak the battery to that upper threshold of the operating range, or is 20793, can you do your abuse testing at ambient?
Depends on your mission, right? We don't pretend an environment or a temperature or even a configuration, right? I think the way we intended to write the requirements anyway is that you would do exactly that. You would analyze your scenario, pick what would be worst case after your survivable number of faults have occurred, and go prove you're safe at that condition.
Yeah. So I'm looking like we're moving up towards the time for the next one. It's 10:45 then. All right. So what I'm gonna do is I'm gonna just wrap this up with showing you all what the end goal is. If you dive into 20793, I was already on the side, sorry. You're going to run abuse testing. I won't get into the weeds of it now, but depending on how you pass or fail your test, there's a certain required number of experiments to be conducted. You're going to try to trigger that pack into thermal runaway with trigger cells that are located in what we believe are worst case scenario locations that would have a higher likelihood of resulting in propagation. And depending on how that battery fails, you may have a full pass, in which case you can just do 3 experiments. You may have a partial pass, in which case you can still pass, but you need 6 experiments, and there's certain criteria that lead you to that. And then you fail, and then that's when everybody just has a really bad day, and then we show up the next day and figure out what to do. Just some examples here. So we've been doing a lot of abuse testing, for example, with our 200 series battery. So we'll play that here. Ultimately, this is very similar to what you want to see. Just smoke exiting the pack. We have no cell-to-cell propagation. You want to have a good table talk, lunch, and discussion. We can talk about those things coming out called sparks and whether or not that constitutes as flame exiting the pack, certainly a point of discussion. And then again, this is our 400 watt-hour pack. This one is poised to be what we believe will be the first off-the-shelf offering of a 20793 battery that you could just order and install on a payload. We're geared up to do 6 of those experiments back to back to back next week, I believe, if not the week after. So we're pretty excited about that. We believe we can achieve a full pass on this design, but we like to always plan for a contingency. So we built 6 test articles up so that we can maintain schedule. So we're excited for that. But with that said, that's what we're trying to do. That's what we're trying to achieve. There's a lot of other things that go into 20793. Find me, find Sam. Happy to discuss it. Yeah.
If I heard correctly, it sounds like NASA's working on revision E. Do we know the changes between revision D and revision E, and are we proactively trying to address the changes between them? So once revision E comes out, we can say that we're certified for revision E?
So I would say that KULR is not in comms with NASA on the development of revision E. That's a primarily internal activity with JSC.
And today, it's the 6 test memo you're talking about. So basically, when we dropped E, it just said you had to characterize the risk and get management approval.
Yeah.
Since we've dropped a memo that defines this 3 test, 6 test, marginal pass, clean pass, it's incorporating that language and then changing critical and catastrophic to H high something battery and mid something. We changed critical and catastrophic nouns to decouple from the safety community. So it's those 2 changes. We haven't had any other adjustments by memo that I know of in the last, since release.
So with that said, I appreciate the interaction. Sam, appreciate the Q&A with Sam. So everybody, Sam.